We've got a nice selection of differentiation rules now to work with. Let's do some further comprehension exercises, now incorporating some problems that also involve the product, the quotient, and the chain rules. All right, we've got these 5 questions here. I'm not going to read them out because that would be extremely tedious, but you can just read them for yourself and pause the video here, take a crack at them with paper and pencil or a whiteboard or whatever you have available, because now I'm going to go over the solutions. All right, for question 1 here, we can take advantage of the product rule to treat these separate parts of the equation as w and z respectively. Then we can calculate the derivative dw dx. We can calculate the derivative dz dx. And now we have all of the pieces we need to take advantage of the product rule formula. So here I've rewritten the formula, but giving some extra space. And we can just plug in terms. So w is w, dz dx is here, z is here, and dw dx is here. So just plug those terms in. And then if you want to, you can go through the fun exercise of multiplying everything out, which is this row here, and then finally simplifying where terms can be added together to give you a final answer of 20x to the power of 4 plus 88x to the power of 3 plus 90x squared. For question 2, we have a fraction, a quotient. So let's take advantage of the quotient rule. To get started, let's split this up into w and z, and then calculate the derivative of w and z with respect to x separately. Once we have those, we can start plugging terms into the equation. So I'm just reproducing what's up here, down here. So z, dw dx, dw dx. And then we're subtracting from that w, dz dx, dz dx. And so that's our numerator. Finally, we need to plug in terms for the denominator, which is z squared. That's just 2 minus x squared. You can leave the denominator as is for the remainder of the solution, or you can expand it out if you'd like to. I'm definitely going to expand in the numerator because there might be opportunities for simplification. So multiplying out all the terms, I get this numerator here. And some of these are like terms, x squared. So negative 12x squared plus 6x squared gives us negative 6x squared. And there you have it, the final simplified answer. All right, for question 3, we have an opportunity to take advantage of the chain rule. Remember, the chain rule allows us to split up our equation into nested parts. So we can consider this inner bit here to be u, 3x plus 1, and we can calculate the derivative of that, which is simply 3. And then separately, we have y equals u squared. The derivative of that is straightforward. dy du is equal to 2u. Now that we have 2u, we can grab u and plug it in for u. Multiply the terms out. 2 times 3x is 6x. 2 times 1 is 2. Now we have all of the terms we need, dy du and du dx, to take advantage of the chain rule. So dy dx is equal to dy du times du dx. The du terms will cancel out. So dy du is 6x plus 2. Du dx is 3. And some pretty simple math here to multiply that out. 3 times 6x is 18x, and 3 times 2 is 6. Nice. Question 4 is another opportunity to take advantage of the chain rule. So we can call x squared plus 5x u, calculate its derivative, du dx, and then separately we have y equals u to the power of 6, and we can calculate dy du u to the power of 6 becomes 6u to the power of 5. And now we can replace u with x squared plus 5x. Just plop it right in there. Now, if you want to, you can expand out this exponent, but it is a lot of work, and it doesn't simplify things further. So I recommend leaving dy du as is when we bring it over into the chain rule here. So just leave it complete. And so multiply dy du times du dx. And that is a good enough answer as it is. Again, trying to expand everything out here is just a huge amount of work with very minimal gain. Okay, and then question 5, yet another opportunity to make use of the chain rule. And here we're chaining together 2 nested equations for a total of 3 equations here. So we've got in the very inside, we've got x to the power of 4 plus 1. So let's call that t. You can call it any variable you like, but I went with t kind of arbitrarily. And you can calculate its derivative, dt dx. Then going one level further out, we have t to the power of 5 plus 7. So t to the power of 5 plus 7, we can calculate that derivative. Becomes 5t to the power of 4. So I'm calling this u, so then du dt is 5t to the power of 4. And we drop in x to the power of 4 plus 1 for t. And then in the outermost equation, we have y is equal to 1 over all of this here, which we can call u. And recalling that y divided by u is equal to u to the power of -1, so it's just the inverse of u. We can calculate dy du, so we move the -1 in front, and we subtract 1 from the exponent, giving us -u to the power of -2. Now we can drop back in u here, so u becomes t to the power of 5 plus 7, and we can also drop in for t. So we can drop x to the power of 4 plus 1 in here, and that gives us this long expression for dy du. But we do now have it. We have our 3 derivatives in our chain. We have dy du, du dt, and dt dx. So we can line these up. Dy dx is equal to dy du times du dt times dt dx. So hopefully you can see what we're doing here, chaining together multiple nested equations. We're going to be doing more of this in the live lessons coming up. So maybe pause the video here and make sure you understand what's happening. We have the du's canceling out here, the dt's canceling out here, leaving us in the end with just dy dx. So we have our 3 different components, our 3 different derivatives. We can simply line them up next to each other now that we have them. dy du is first, and then du dt, and finally dt dx. All right, that's the answer. Nice, so hopefully you enjoyed working through those exercises and you're starting to feel like you have a good grip on all of the derivative rules that we've followed so far. I've just got one more rule coming up that will simplify some of the work that we've been doing very recently in these exercises.